Hello everyone, I'm Jiang from the Department of Precision Engineering, the University of Tokyo. And in this presentation, I'd like to talk about my research, glass confidence grid map building using laser rangefinder on mobile robot. First of all, as background, a map of the environment is essential for mobile robots. And the mobile robots usually use simultaneous localization and mapping, or SLAM, to build maps of their environment. In this video, a robot car is using laser rangefinder to measure the distance to the objects and building the map and localizing itself at the same time. Laser rangefinders are widely used for mobile robot SLAM. It's a distance measuring sensor, and it can emit a beam of light which will be reflected by the surface of the object. Because the objects in daily life environment are usually not perfectly smooth, so the laser usually be reflected in a diffusive way, which means it will be reflected into all directions. So the sensor can also receive a beam of reflected light. By recording the time of flight, it can calculate the distance to the object. However, laser rangefinder can only detect glass from certain instant angles. We performed a simple experiment to show this phenomenon. We fixed a sensor on a laser rangefinder on a mobile robot and have the robot move along the corridor. The white points in the video should be the outline of the objects or the 2D map of the environment. And as you can see that the wall can be detected stably from any direction and instant angles, while the glass can only be detected when the robot moves near to it. The far glass cannot be detected by the sensor. There are two reasons for it. The first one is that the glass is transparent, and so most of the light will penetrate it instead of being reflected. And the second reason is that the surface of the glass is much smoother than surface of wall, so some of the light will be reflected in a specular way, not a diffusive way. So the sensor cannot receive the reflected light and will think there is nothing in front of it. There are several problems caused by this glass detection failure. The first one is bad map. For human, we can easily tell that there are glass walls along the corridor in the photo shown on the left. And the correct map should be the one shown in the middle. While in the map generated by the SLAM program, the glass disappeared completely. As the robot cannot see the glass, it can easily run into it. The last problem is that because the robot localizes itself by comparing the current measurement of the environment and the information or the shape in the map. If the measurement of the environment keeps changing and is unreliable, the robot will be confused where it is, which will negatively influence the localization accuracy. So our research aim is to detect glass in human indoor environments using laser rangefinder and build glass confidence grid maps. In the grid map, all of the objects are simplified into two types, walls and glass. And the possibility of being wall or glass is calculated and shown in the map by changing color. So the first step of our research is detect the glass, and we propose two methods for it. The first one is using multi-echo laser rangefinder. So what is a multi-echo laser rangefinder? When a laser rangefinder is facing a glass which is in front of a wall, its laser beam will be reflected twice in fact. However, a single echo laser rangefinder or a normal laser rangefinder will only report one echo, usually the one with highest intensity, so we can only get the distance to the wall. While For a multi-echo laser rangefinder, it will receive both echoes, so we can get both the distance to the glass and to the wall. And as proposed in Koch's research published this year, glass can be detected by comparing the measured distance of the two echoes. If the difference of distance of two echoes is higher than a threshold, the points of first echo should be glass. Else, if not, we don't know. In that situation, we can still use the method 2, analyzing scan intensity. Scan intensity is the strength of the received reflected light. And the reason why we use scan intensity is that we find that for the same point, as the incident angle changes, the scan intensity also changes. And the way how it changes is different for wall and glass. So for a certain point, if we can get the intensity distribution patterns, we can predict whether it's wall or glass. The last question is that how can we get the scan intensity distribution patterns? Take this point or grid as an example. The sensor on the robot scans the environment from right to the left, and there will be one beam of laser will hit this grid, so we can get the intensity of for a certain instant angle. And as the robot moves, the instant angle also changes. We can get the distance for different instant angles. And if we keep the robot moving and scanning, we can get the whole distribution patterns for this point. And it's completely same for other points in this environment. So our approach is that for all grids or all points in the world, we get the laser data and use method 1, check the distance of two echoes, then calculate and update the confidence. Also, we use method 2 to fit the intensity distribution pattern and calculate and update the confidence. Then we show it in map. And after this loop, we go to the next scan. Finally, we performed an experiment to show the feasibility of our approach. We used the Hakuyo multi-echo sensor and the Pioneer mobile robot. We have the sensor scan the environment and have the robot move forward for 10 centimeters and then scan and then move forward. In this experiment, we move the robot and measure the distance manually because we want to get the ground truth of the distance. And we took the data for 55 positions in total, and then use the data to build the glass confidence grid map for this environment. As you can see in this video that wall can be detected from far distance and is much earlier than glass. For glass, sometimes is initially detected as wall, but is updated into glass quickly. It turns out that our approach has high accuracy because it can correctly detect the mantle frame of the glass. As for the noisy area at the left bottom, it is caused by the fire extinguisher. Finally, in the conclusion and future work, our method can distinguish between wall and glass and build an accurate confidence grid map. And wall can be detected and marked on the map from a further distance and a larger range of instant angles than glass. About future work, as I mentioned before, that now we measured and move the robot manually, but later we'd like to combine our approach with the SLAM program so that we can do all of this automatically. And also, we'd like to challenge in a more complex glass environment to test our approach. Okay, thank you for your attention.